All right, so let me show you an application of some of this work. Fairly simple application, and I'm actually going to give you a lot of the information up front, and then we're just going to work our way to a solution. So the application reads as follows. It says an ice tray, in an ice tray, the water level in any particular ice cube cell will change at a rate proportional to the difference between the cell's water level and the level in the adjacent cells. Okay, so this is your ice tray, and in this particular ice tray there's only 3 cells, right? So you can make 3 ice cubes with this ice tray. And let's kind of notice, like from the picture, so your X and your Y and your Z basically represent the water levels in that cell, right? And that would be the water levels at some time t. All right, now they tell us the relationship of dx dt, dy dt, dz dt. Without much elaboration on this, but what they're saying is, look, the change in water level for cell X is basically going to be equal to the water levels in Y minus the water levels in X. And I'm not going to go into, you can just imagine you have water, I assume water pouring into this ice tray, and of course you're going to have some spillover, right? Certain cells are going to spill over into the other cells, you know how when you fill up an ice tray. But nevertheless, this is our system of differential equations. And now what I want to do is I want to go from here to the normal form, and then I'm just going to give you the eigenvalues and eigenvectors as well as an initial condition, and we'll solve it, okay? So let's go ahead and go from the set of differential equations to our model for these water levels, right? So how can we think about this in terms of a matrix? Well, we know that in this case it would be x prime is all going to be equal to y prime z prime. All of this falls under the heading x prime. Okay, now I don't mean to use x prime twice but this is the form that we've been using all along. So I'll continue to use it, okay? All right, so let me clean that up just a little bit. That's x prime. All right, and now, so that's going to be equal to, so let's figure out what matrix A would be. And then we got to figure out what our vector would be. So in this case, let's go ahead and do A. So what we're going to do is we're just going to, we're looking at the right-hand side of these differential equations, and we're just going to, just starting, letting it go x, y, z. We're going to start with the fact that there's negative x in the first row, there's 1 y, and there's 0 z. All right, so this would be negative 1. So we got negative 1, then 1, then 0. All right, now let's look at the second row. So we have 1x, we have negative 2y, and we have 1z. All right, just make sure you're going in order, not the order that it's written necessarily, right? So I can see that when they wrote it this way, that's kind of a little trap. They're hoping that you'll write 1, 1, negative 2, but you're spotting that's 1, negative 2, 1. All right, and finally, for that last equation, which would be our last row, we have 0 x's, we have 1 y, and we have a negative 1 z. Okay, now the variables that you're just look at the only variables being used here are x, y, and z. So this is our x prime is equal to a multiplied by x. Okay, so at this stage, I'm going to come in and save us some time. So it says use the eigenvectors to solve for the initial condition. Now, normally what you would do is I would, in a question like this on a test, remember, since that's a 3 by 3 matrix, I would go ahead and give you the eigenvalues, which are -3, -1, and 0. And this would be enough for you to find the eigenvectors. But for this application, I'm just going to go ahead and give you the eigenvectors as well. So 1, -2, 1. -1, 0, 1. And 1, 1, 1. All right, so those are the eigenvectors associated with those eigenvalues. And now let's interpret this initial condition. So x sub 0, y sub 0, z sub 0. So that's nice. That's nice that they let it t be 0. And we have x sub 0 is 3, y, not sub 0, but y of 0 is 0, and z of 0 is 0. Okay, so let me go ahead and go from, I'm going to kind of grab this and drop it right here. So that's our initial conditions. And now what I'm going to do is I'm going to go ahead and set up the general solution first. Okay? So all that you need is these eigenvectors and these eigenvalues to get to the general solution. But we'll need to do a little bit more work to get to the particular solution. So let's go ahead and do the general solution. So c sub 1 e to the -3t multiplied by 1, -2, 1 plus c sub 2 e to the -t multiplied by -1, 0, 1. Now, this would be plus c sub 3. Now, it would be e to the 0, but e to the 0 is just 1. So that would be times 1, 1, 1. Okay, so that is our general solution, right? So that's a general solution to our homogeneous equation. And now we're going to go to the particular solution using these initial values. All right, so the good news is, again, because they're letting t equal 0, let's go ahead and set it up. So it's going to end up being a multiplied by c is equal to this initial value, 3, 0, 0. All right, now the only difference is, of course, the c is represented as c sub 1, c sub 2, c sub 3. And the good news is, since this is at time 0, all right, time 0, we can just simply take our matrix A that we used previously, which is just the not the matrix that we used previously, I'm sorry, but the matrix that's formed from the eigenvectors will be a quick way of finding A in this scenario. So, all right, well, we end up with 1, -2, 1, -1, 0, 1, 1, 1, 1, and that's going to be times, let's go ahead and write C as C sub 1, C sub 2, C sub 3, and that's got to be equal to 3, 0, 0, okay? So that's, again, just pay attention to how, when I give you initial values like this, that translates into an initial value like this. All right, well, at this case, I've already shown you how to do this. You would take A, set it equal to your 3, 0, 0, you would row reduce, and you would figure out that you end up with the following. Well, let me go ahead and rewrite it. You end up with the following. So C sub 1 being equal to 1/2, C sub 2 being equal to -3/2, and then you just have C sub 3 being equal to 1. All right, and now it's your job, not my job right now, but your job to go ahead and plug that in to your general solution so that you have your particular solution. Okay? I can punt on this because, well, I've already studied this stuff. All right. Now, what you have seen is, let me see if I can back up for just a second. I want to show you all the eigenvalues that you have dealt with so far have all been distinct, right? So eigenvalues such as like 1, -1, 2. I want to figure out, well, what do we do when we have two eigenvalues that are the same, right? So you can kind of think about this as, what do we do when, if you think about, we had scenarios where you would have t e to the rt or t squared e to the rt, and the general solutions to, depending on your discriminant, right? Are they distinct and real? Are they real but not distinct? Are they complex but distinct? So there were some different sections back in chapter 4 address these different topics. So I want to now show you how you address a scenario where you do get two roots that are or eigenvectors basically associated with the same root twice. And let me now go ahead and walk you through this problem. So what we want to do is, again, we're sticking with homogeneous for right now. We want to find the general solution to the following differential system. And here we are given A. All right, now A is a 3 by 3, so that means I would give you, on the test, I would give you your eigenvalues. Well, here are your eigenvalues. All right, well, let's start with the fact that we are noticing that two of the eigenvalues are the same. Let's start with that, finding the eigenvector associated with that eigenvalue of 3. All right, again, I'm taking the liberty to get a lot of this out of the way all up front. So it's up to you to pause the video if you want to write all this down, so you don't have to listen to me talk over your writing. But you remember, when we're going to jump right into A minus 3i, which is right, so the identity matrix I. I went ahead and did that, so that's what we have here. And then here's our C. Again, since at this stage it's set equal to 0, so we just take our A with set equal to an augmented matrix set equal to 0, RREF. That gets us to the following, okay? And now from here, let's actually get to our system, and get back to our system, and then we'll get back to our eigenvectors. Ready? So some students fail to see how to go from this step to this next step. But look, it's very simple. It's just, you have 1 times C sub 1, rows times columns, 1 times C sub 2, then -1 times C sub 3. So that gives us what? That gives us C sub 1 plus C sub 2 minus C sub 3 being equal to 0. All right. So let me give myself a little bit of space, and you can just kind of follow me up here. All right, so clearly what we have is we only have one pivot position, so we only have one basic variable. These are both free variables, okay? So let's go ahead and write that. So that would mean at this stage, you can solve for your basic variable. So C sub 1 is equal to negative C sub 2 plus C sub 3. And now the question then becomes, well, how do I set up my vectors, right? Because you're not choosing values to plug in for your vectors. So it would look like this. So C sub 1 is equal to negative C sub 2 plus C sub 3. C sub 2 is free. C sub 3 is free. All right, so that's our description. All right, so now the way you can kind of follow me as I go through this fashion, we're almost there. So you can think about that matrix as this is C sub 1 first, right? So C sub 1 is, let's write everything in terms of our free variables. So this is negative C sub 2 plus C sub 3. C sub 2 is our second row, and C sub 3 is our third row, right? Isn't that what we have here? C sub 1, then C sub 2, then C sub 3? Well, C sub 1 is written in terms of its free variables this way, and then here's C sub 2, and here's C sub 3. All right. Well, when we do linear combinations, they end up being, the free variables end up being the scalars of the vectors, and the vectors in this case are going to be our eigenvectors. All right, so here we go. So if you were to factor out a C sub 2, right, you can think about breaking it up if you'd like. You can think about breaking this up into the following, and then let's figure out what would be left. So how many let's look at the very first row. Right, so let's figure out what goes here. So the very first row, how many C sub 2s are there? Well, there's negative 1 of them. All right, and this one, how many C sub 2s are in the second row? 1. And how many C sub 2s are in the third row? 0. So that ends up being negative 1, 1, 0. Now let's do the same thing for C sub 3. So how many C sub 3s are in the first row? 1. How many C sub 3s in the second row? 0. How many C sub 3s in the third row? 1. So we end up with 1, 0, 1. All right, there it is. Notice that you got 2 eigenvectors, and that makes for this 1 eigenvalue. And that makes sense because it's that same eigenvalue is listed twice. Okay, so we will come back to those eigenvectors, and we'll put them to use in just a second. I'm going to kind of rush this process. So using that last eigenvalue of negative 3, you can go through, you can, we have RREF'd this matrix. Let's get back to a system. So this would be C sub 1 plus C sub 2 is equal to 0. Then we would have C sub 2 plus C sub 3 is equal to 0. And there's no need to state 0 is equal to 0. So at this stage, we solve. Notice that you have 2 basic variables and 1 free variable. Let's go ahead and solve for our basic variables. So we would have C sub 1 is equal to negative C sub 3. C sub 2 is equal to negative, also negative C sub 3. Did I do something incorrectly? I think I did, didn't I? Yeah, that should be, so we have 1 C sub 1, and what I should is 1 C sub 3. That's what I should have here. So, and then C sub 2 is also equal to negative C sub 3. All right, so in this case, you can choose a value. So we can, for C sub 3. So we can let C sub 3 equal 1. So that if that's the case, that would mean that C sub 1 is equal to negative 1. And that would also mean that C sub 2 is equal to negative 1. All right, so what is the eigenvector here? Well, remember it's C sub 1, C sub 2, C sub 3. And we chose 1 for C sub 3. And the result was negative 1 for C sub 1 and C sub 2. Okay, so let's now form the general solution. So the general solution, x of t, is going to be equal to C sub 1 e to the, so positive 3t. And I'll have to go to the previous page and grab those vectors. plus c sub 2 e to the 3t plus, let me come down here, c sub 3 e to the negative 3t, and I actually do know that vector, the eigenvector, negative 1, negative 1, 1. Okay, so now the only thing I have to do is go to the previous page and grab these two vectors. So negative 1, 1, 0, 1, 0, 1. So negative 1, 1, 0, 1, 0, 1. And that's it. That is your general solution. You can't go any farther unless somebody gives you a little bit more information. All right. So at this stage, we have covered this last problem was when you have, think of like the double root, when you end up with having the same root show up twice. In this case, we have the same eigenvalue show up twice. We've also done multiple problems when you have distinct eigenvalues. And I'm going to skip over the section when you have complex eigenvalues. All right, so that is something that you won't be asked to do on the test. And the last bit of material, which we'll take a break and then we'll come back, and the last bit of material is going to be to study non-homogeneous linear systems. So how do we deal with this f of t, this function of t? So when it's not equal to 0, the non-homogeneous case. And that's what we'll do when we get back.